Okay, the people I do not see here are Jaron, Cassie, and Helena. Okay. Tori just mentioned a problem that has a galvanometer in it with a bridge. That would be number 4. And so let's talk about that just for a brief instant before we go into magnetism. So problem number 4. Take a picture. Got to turn it upside down. Works better without your hand over it. Trust me, you guys have no faith, do you? Okay. See? Got to have a little faith. George Michael sang about that. So, we have this problem, a Wheatstone bridge. A Wheatstone bridge is something that is a very sensitive circuit that allows you to make measurements of resistance. And so the goal is to have this galvanometer read 0 current. So you close this switch. As long as that switch is open, of course it reads nothing. But when it has no current going through, then you know for sure if there's no current through a resistor, what does that tell you about the voltage difference across it? Okay, there's no voltage difference across that resistor that's RG, the resistance of the galvanometer, and hence the voltage at A is equal to the voltage at D. So that was the whole point of this. You've adjusted so you have the voltage at A is equal to the voltage at D. And when that case occurs, it is equivalent to doing this to your circuit. Taking that out. So there's no connection. And so what you're really doing is solving the circuit so it's like that. And you know that voltage B is equal to voltage D. So if you take the currents and in this case you have the same voltage across both sides, and the current is going to be that total voltage divided by the series combination R12 for the one side, voltage divided by the series combination R3, Rx on the other side. So you can calculate the two currents, and then if you want to find the voltage B, if I know that the, oh, I forgot this lowercase r, so you have to take that into account. My bad. You know what doesn't matter? Doesn't matter what this lowercase r is or what the D is. The stuff in my little, I can't do that. The stuff inside here does not matter. Just say I have some voltage V, unless it actually asks you for the current, which it doesn't in part A. And there's only a part A. It doesn't even matter what it is. So you could just say the voltage out of this box is 10 volts, or V. And then you find the current in terms of that, and then just say, okay, well, I'm going to consider this 0 voltage here, that is, I'm going to put my reference there, and the voltage at D is going to be current 1 times R2. And the voltage at B is current 1 times Rx, or current 2, excuse me, times Rx. And you know those two have to equal each other. You could also say the voltage at D is the positive voltage here, V, minus I1R1. And the voltage at B is this minus I2R3. And so you have a set of equations that allows you to relate what R3 and Rx have to be. So there's the trickiness in there's a galvanometer here, and I never talked about the galvanometer, nor am I going to talk about the galvanometer. But as long as you understand that the whole key is when it's balanced, it's like that's not there, and you just have two parallel paths, you can do that. So does that make it easier to understand? Okay, I saw a couple, 3 affirmative nods. That, makes me feel better. Okay, so I put that right on top of my... no, I didn't. There's my opening pretty picture. Magnetism. Wait, before I talk about magnetism, there's something else that I talked about once, and then I dropped it and never brought it back, and that's power in an electric circuit. We talked about power specifically in the case of a capacitor. And we determined when we were looking at the capacitor that the power, well, that the energy is charge multiplied by the voltage difference it goes through. Right, so we learned with the capacitor, the change in potential energy is Q times the change in potential energy. Not change in potential energy, change in V. And so power is defined as power is equal to delta U over delta T, the rate at which energy is converted. So if I divide the delta U by delta T, what do I have to do on the other side of the equal sign? Divide by delta T. But current is equal to Q over delta T, so that means power is equal to current times voltage. And I'm pretty sure I said that at one point, but I didn't make it a point of emphasis. I've skipped all of the homework problems that had power in them because each time I looked at homework problems, I'm like, you know, I didn't spend enough time actually saying the power consumed by a resistor is the current through the resistor multiplied by the voltage drop. And it's consumed because it takes energy out, and you can look at the direction of the current and the direction of the voltage to determine that it's consumed. For a battery or a power supply, it's still power is current times voltage, but because the current comes out of the positive side of a battery, it's producing power. So if current comes out of the positive side, it's producing power. Current comes out of the negative side, it's absorbing power. So anytime we talk about power in an electric circuit, you just have this IV relationship. If you have a resistive material, you can use Ohm's law to say power is equal to I, and since V equals IR, I'll just put like that. So that's I squared R. Or you can say I is V over R. It's equal to V squared over R. So for a resistor, those two are also equivalent. But don't get confused and try to use those two on a power supply, because the power supply should have a resistance there. That's only true if you have Ohm's law available. So for a resistor, that's how you calculate the power. I know we talked about it really briefly, but I want to make sure you have that as well. I told, I think, Austin, the stuff in the test was through what we covered on Wednesday, except for this. We need to know how to do the power in a circuit. And it's really straightforward. If you know the current and the voltage, you know how to do the power. Excuse me? Yeah, circuits will be on the test, yes. Yes, everything through Wednesday plus this, the power. But not the pretty magnet pictures. So let's look at these pretty pictures. What does one picture have to do with the other picture? Must be some relation or I wouldn't have the two pictures. What is the picture on the right? Okay. Well, it could be Aurora Borealis or Aurora Australis. Australis for south, Borealis for north. Had to think about that. Almost certainly, though, it's Borealis, northern lights. The northern lights are caused by having charged particles coming from the sun fly through the Earth's atmosphere. And the Earth's magnetic field redirects the motion of charged particles so that if you're close to the equator, they're not going to hit you. But if you're closer to the pole, the Earth's magnetic fields will actually bring those charged particles into you and direct them at you. And so near the poles, you have charged particles that come flying into the Earth's atmosphere because of the Earth's magnetic field. And so it's the Earth's magnetic field that makes the northern and southern lights and not, a global phenomenon. So we'll learn more about that by hopefully the end of today. Depends on, the pace of the lecture. Okay, so magnetic fields. We've talked about electric fields. What did I use to help you understand and feel more comfortable with electric fields? Gravity, gravitational fields. We talked about gravitational fields. When I first introduced it, I made sure I said the word gravitational field, but probably most people completely forgot about that. We just talked about the acceleration of gravity. But the field is a concept for helping us deal with forces. So we call it a force field. Gravitational field is a force field. You hear force field and you think more Star Trek. Then you think, real. But Star Trek actually has a lot of pretty good physics in it. And force fields, antimatter, good ideas. Antimatter would be great for your propulsion system if you could contain it. So how do they contain their antimatter? In a dilithium crystal, which doesn't exist. Which is too bad. I mean, our little smartphones, these are essentially the little, whatever they called their things, they communicated with them and could look up the dictionary. It seems so marvelous back in the 70s. And now we actually have that, and you guys probably just take it for granted, like, well, duh. Anyway. So, we talked about electric field as a way to help us understand and deal with calculations of force and later energy with electricity. Electric fields are there for just those purposes, working with the force and the energy. Now we get to magnetism. The history of our understanding of magnetism is rather interesting. The first known historical magnets were in China, and they were used, as novelty things in games. Now, some people say, that's degrading the Chinese people, saying that they were using them as novelties in games. No, everything was used as novelty in games. Telescopes were first used as novelty in games, too. Doesn't degrade you coming up with this cool thing. The story of magnets and how it got its name is very questionable, but yet here it is. There was a shepherd boy in the region of Magnesia. How many people knew there was a region on Earth called Magnesia? It wasn't just milk or a source of milk.
Only because of the reading.
Only because of the reading. So he has this little staff that has a metal tip on it, and he notices, hey, there's some rocks here that stick to the tip of my staff. And woo! Some kind of magic that comes from Magnesia. And they got the name magnet from the region Magnesia. So the story goes. The story I stop. Yeah, very questionable. So, what was understood about magnetism? For a very long period of time, virtually nothing. For a very long period of time, it was thought to be basically some kind of magic. And so, people would talk about, you've heard of animal magnetism, and they thought that this was all just some kind of voodoo, hocus pocus. But people noticed cool things. Magnets do stuff that's fun. So I can take a magnet and pick something up. Now I have two of these. Okay, they both picked it up. One is, that side won't pick it up. Crummy magnet, right? This picks it up with that one. Picks it up with that one. Both sides pick it up. Better magnet. Magnets have two poles, so I can do things like just do these two. Austin, because he's had fun separating magnets in the past. Okay, I have these magnets, and clearly, if I put them like this, they attract. If I take them, pick them apart. Austin, ready? Turn one of them around and bring them together, what's going to happen? They don't attract, they repel. So if they attract one way and repel the other, what does that tell you about magnets? Okay. that they must not be like mass, which is unipolar. Mass is unipolar, it has one pole. So we just say the mass charge, the gravitational charge is just mass and it's always a positive value. With electric charge, it was a dipole. We had positive charge and negative charge. With magnets, we once again have a dipole, two charges. And so with magnets, we don't want to use the same thing we use with electricity. In electricity, they randomly chose positive and negative. So with magnets, we talk about the two poles being north and south. I know Sally and I talked about this. How did they get the names north and south? Wasn't it you that I talked this with, Sally? How did they get the names?
Oh no.
What's with you? He just doesn't want to answer. Oh no, we didn't talk about this. We never talked about this. They noticed that if you take a magnet and you make it free to rotate, one side will seek the North Pole. So it's a north-seeking side. And they said, well, let's call the side that seeks north, north. And let's call the side that seeks south, south. Then with some more experimentation, take your magnets, and here I have some magnets that, by the way, this is how you should store magnets. I have a piece of wood between them so they can't touch each other. And then there's a little piece of steel on each end that we call a keeper. I'll talk about why in a minute. So I take these, and I actually set these up correctly. So I have the north side, and I'll put the north side here to the north-seeking side of the compass. So this is north-seeking, and that's north-seeking. And when I bring them up, sure, okay. Chad, this is your job, Chad. Chad, your job is to hold this.
I'm sure.
I know, it's tough. It's tough. So everybody can see, right? So I bring the north up here, and it pulls the south-seeking side to the north. If I flip this around to the south, the north-seeking side goes toward the south. So, what does that tell you? Thank you, Chad. I'll call on you again. Yeah, you're welcome. So what does that tell you if the north-seeking side is attracted to south? Or, excuse me. Yes, attracted to south. That's right. Okay. Just like with electric charge, the opposites attract. So now I have the Earth. Go back a slide. So we have the Earth. And I have a compass that I put right here. And my north-seeking side is pointing toward the North Pole, but it has to point toward the South Pole of a magnet. And so it turns out that the north geographic pole is the south magnetic pole. Because they named it north-seeking, but because north seeks south, it turns out to be flipped. Oh, this isn't the worst thing, though. Here's the worst thing. We now understand that every approximately 13 years, the magnetic poles of the sun flip. So the sun has a north and south pole, and periodically they flip. In fact, weirdest of all is that during recent, notice somebody's made an electric motor right here. That's basically what you're doing with an electric motor. For a brief period of time, the sun had two north poles and north-south pole, which, as we'll talk about in a minute, seems wrong, but through experimentation with the magnets we used to stick in cows to attract all of the wires that happened to be in the hay that we didn't carefully remove when we cut the wires from the bales of hay, those also only had one pole. And no, it's not Nobel-worthy physics, sadly. So, where was I? Oh, yes. The Earth's magnetic field also flips poles. Approximately every 200,000 years, that's an average, the Earth's north and south magnetic poles flip. And it's been nearly 1 million years since the last time the Earth's north and south poles have flipped. So sometime soon, we can't say how long, but we should expect the Earth's magnetic poles to flip, and then the north geographic pole will be a north magnetic pole. And the north-seeking side of the compass will point south. Okay, fun to know, right? Sure. Well, how do these field lines work, and what's the point of an electric field line? Magnetic field lines are the magnetic equivalent of electric field lines. They're lines of force. But magnets are a lot more bizarre than the other things we've worked with. So these magnetic fields are not as simple to understand as electric fields. And I'm sure right about now you're like, wait a minute, did he say electric fields were simple? Well, comparatively, yes, they are. So, thank you. Things about magnetic field lines. Number one, as far as we know, there is no such thing as a magnetic monopole. Charge comes, you can have a negative charge, i.e. an electron, positive charge, proton, no problems. But magnetic charge never comes as a monopole. It always comes as a dipole, so that your net magnetic strength is always zero. So magnetic field lines do essentially the same things as electric field lines do. Electric field lines always went out of what? Went out of positive and went into negative. Magnetic field lines do the same thing. They come out of positive and go into negative, except for positive we now call north, and negative we call south. So the magnetic field lines come out of the north of a magnet and go into the south of a magnet. But because magnets always come as dipoles, the magnetic field lines never end. Right? Electric field lines could end at infinity, or they could end at a charge. Magnetic field lines always make loops. So if you look at this picture, you see that you had magnetic field lines coming out of north, going down to south, and then cycling back through the magnet and coming out again. So magnetic field lines always loop. That's why we store the magnets the way I showed you, having the keepers at both ends and the wood in between. That way the magnetic field lines, if you have them aligned like that, so it was north, south, south, north, with those keepers at the ends. What you're doing with those keepers is keeping the magnetic field concentrated. So with that arrangement, the magnetic field lines are just doing a loop like this and staying internal to your material. And that helps to keep the magnetism strong in the material. Now we're going to talk about what creates magnetism here in just a minute and how that helps to keep them strong. But that's why you should store them that way. We'll also talk about how you can rejuvenate a magnet, which is really cool, right? I can take before class, I rejuvenated these things so they would work, because before I bought that thing, I had lots of bar magnets. I'm like, well, this doesn't work, this doesn't work, this doesn't work, because they're not the greatest of bar magnets. So, magnetic fields, the only thing on here that I haven't talked about is this bottom statement. We use the symbol B for magnetic field. Now you might say, B, why B? And I would say, well, it's better than H, because we also use that for magnetic field. We use B and H and, I think there's one more, D, depending on your situation. So none of those are M, because M is used for magnetic moment. So B is the unit for magnetic field, is the symbol for magnetic field, and the units of magnetic field are Teslas. Now, right now, I'm just going to give you that. The units are Teslas. Later on, we'll see what a Tesla is. And of course, it's named after Nikola Tesla. There is another common unit that is used for magnetic field, that's the Gauss. And a Gauss is just 1/10,000th of a Tesla. And so 1 Gauss equals 10 to the minus 4 Tesla. I think it's capital G for Gauss. What?
Gauss.
Gauss, G-A-U-S-S. Like Gauss's law, Gauss. So those are the units that we use. The Gauss is not the standard SI unit. The Tesla is the standard SI unit. Okay, more about magnets. We got 20 minutes. Those magnetic field lines, because they go out of the north and into the south, we can map them and see how they travel. Now, going back 2 slides, pretty picture, this showed a drawing of magnetic field lines, and this picture over here, you have iron filings. Iron is a strongly magnetic material. Strongly magnetic materials we call ferromagnets. Iron doesn't mean strong. Ferromagnet means it's magnetic like iron, because ferro means iron. So ferromagnets are strong magnets, not the strongest, but they're strong. And because we have these little pieces of iron, each little piece of iron will behave like a magnet, and so they are attracted. Remember, opposites attract. The north was attracted to the south. And so the north side of a little magnet is attracted to the south, and each one of these little filings is following along the magnetic field lines. And this brings up our first interesting thing about magnetic force. Magnetic force will create a torque to make magnets align. What is a torque? I've talked about this. I'm not asking some rhetorical question that you don't know the answer to. What is a torque? Okay, it's a twisting kind of force. So the torque is going to make something rotate, and then, of course, it does pull as well. You've seen magnets pull things together. But that torque, it'll make things rotate, and that's what Chad was using to make his little electric motor here. He was using a magnet to make it rotate because of that torque. Actually, I think I wanted to go one further than this, but let's see where So now that idea of having only one magnetic pole. Remember I said the sun for a brief period of time had 2 north poles, and those cow magnets we used to use had the same pole on both sides. How does that work? Well, first of all, magnetism is a quantum physics phenomenon. It has to do with the magnetic moments of electrons, of orbitals, of protons, and of neutrons. And of course, you're very comfortable and familiar with the magnetic moments of electrons and possibly protons and neutrons. What do we call that?
Say the question again.
The magnetic moment of an electron. You talk about it all the time in chemistry.
Polar?
Charge.
Diamagnetic?
The spin. The spin has nothing to do with spinning. It was initially thought it might be caused by an electron spinning. Scientists used to think that electrons actually physically, were spinning. Well, now we are quite confident they are not spinning. The spin is simply a measurement of their magnetic dipole moment. That is, how strong a magnet they are and how they're aligned. All electrons are the same strength of magnet, but they can be aligned differently. And so when we talk about the spin, that's what we're talking about. It's the magnetic moment of the electron. But protons also have a spin. They also have a magnetic moment. The geomagnetic ratio is different for a proton and an electron. So a proton that spin up does not have the same magnetic field as an electron that spin up. They're different, but there's a little ratio that connects the actual magnetic moment to the spin. That's what's causing magnetism. And so different types of materials that have a different number of nucleons are going to have different magnetic behavior. And atomic orbitals will give them different magnetic behavior, so that if you have a completely filled shell, you're going to have very little magnetism. So, I mean, how many people knew that that's what magnetism was about? Right? You tend to just think it's materials. And a lot of, what were you saying, Tori?
We talk about paramagnetic versus diamagnetic in chemistry. So.
Oh, you do? Good. Good, because I'm talking about it in like 2 slides. But I am not talking about the quantum physics of it. Just in case anyone was worried. So with our understanding of the dipoles, if you take a magnet and break it in half, you don't have the north half and the south half. The north half is going to have a north side and a south side. The south half will have a north side and a south side. And you can keep doing that almost infinitely, until you get down to a single molecule. And the single molecule will have the north side and the south side. And so you never can cut it and just get the north part or just get the south part. You're always going to have the magnetic dipole together. And so hence the statement, as far as we know, there are no magnetic monopoles. Now, if you studied cosmology, which I'm sure none of you did, Guth was actually studying magnetic monopoles. And according to physics calculations, it's possible for a magnetic monopole to exist. And if you read Guth's book, he's really kind of funny. Because he says, I did the calculations, and in order to create a high enough energy to create a magnetic monopole, I would need a particle accelerator that goes outside of the Milky Way galaxy, I think it is. And the US government just wouldn't fund that research. And so that got him to thinking about where could you have enough energy to create a magnetic monopole. And his final conclusion was, well, the energy released in the Big Bang would be enough to theoretically make 7 magnetic monopoles. So there might be 7 magnetic monopoles spread out throughout the entire infinite universe. All we really need to do is start searching. Yeah, I think you all understand that would be a rather fruitless search. So we say, as far as we know, there's no such thing as a magnetic monopole. It's possible that one could exist. Extremely unlikely that we would ever find one. So for your take home, just say there are no magnetic monopoles, because if it's ever found that one exists, the whole world will know, because they will be struck with all these headlines that say, earth-shattering discovery. And most people not taking physics will say, what? Look, I got a magnet here. It has a north on it. What's so special about that? It's because, yeah. Okay, moving forward. Oh, I already said that one. One of the problems with having slides is you speak in an order, and then you come to these, and you're like, well, did that one, did that one, did that one. So, moving past. Already talked about this. By the way, it is a fictitious magnet inside the Earth. There's not a real bar magnet inside the Earth. In fact, as we understand, well, first of all, we have never been able to penetrate the outermost layer of the Earth. The Earth has its layers, the crust, and then underneath the crust you have the mantle, which is broken up into the upper part and the lower parts of the mantle. And then you have the liquid and the solid core. We've never been able to penetrate the crust, which at its thinnest is about 7 kilometers thick. The reason we can't is it gets so hot that the drills melt. So a lot of work has been done to try to drill through and get to the mantle so we can understand it better. But everything we know is based on seismic measurements and models based on our understanding of physics. And our understanding of physics says that the Earth's magnetic field must be, created by what we call the Geodynamo, by molten metals that conduct electricity swirling around in the core of the Earth. And you also have to have convection here. What is convection? Okay, transfer of heat by the motion of small particles. The hotter materials float outward, the cooler ones float inward. So you have to have convection in that swirling, molten, conducting material. If you have conducting material swirling in circles with convection, it'll create a magnetic field. And we believe that's what creates the Earth's magnetic field. We call it the geodynamo. And so the magnetic field reflects that. Because the magnetic field is created by swirling material, you can understand it doesn't have to be stable. Something outside could cause interference with that swirling material. And in fact, the Earth's magnetic field itself can interfere with other material that's swirling and cause it to get jumbled up. And it's believed that's what causes the flipping of the magnetic fields. The sun is much larger, has a much stronger magnetic field, and because of that, its magnetic fields flip much more often than ours do. So, just want everybody to understand. Not a bar magnet in there. When it flips, it's not going to go. Okay, first clicker question. Which magnetic pole is the Earth's north geographic pole? And you can answer now. There is a prominent answer and a secondary answer that one could consider. Right? These kind of questions are not like test questions. If you think it through and have a different answer than the one I chose, that's fine. Okay, everybody has answered. So the answers we had were 0, 13, 0, 0, 4. Now, since Chad was the one who brought this up, which one did you choose, Chad?
Well, I chose south.
Okay, he chose south. South is what most people chose. Why did you choose south?
Because currently that is correct.
Currently, that is correct. As north seeking means that it's pointing towards south, and hence it's a south. You were thinking, though, about answering this one, right? Because that's also true. If I had said, what was the Earth's north geographic pole a million years ago, the answer would have been, oh, it was north. So that you could defend either one of those answers. Clearly on an exam, I would say, what is currently? And then there's no question about the correct answer. Okay, magnetic materials. Strongly magnetic materials are called ferromagnetic, and iron is, of course, where it gets its name. Other ferromagnetic materials, nickel, cobalt, chromium dioxide. None of you guys are old enough to have gone out and purchased that Devo tape on a cassette. But cassette tapes, they would say like, chromium 2, chromium 3. And what they were talking about was, you have the different oxidation states of the chromium oxides, and they give you a different magnetism. And the way those tapes worked is you had, of course, your celluloid as just a base. Is celluloid, right? The stuff that tape is made out of? Like this? I think it is. Yes. Okay, so you have Scott's tape down there. And then on top of that, you have a gel. And in that gel, you have flecks of some magnetic material. It could be iron filings, or those tapes, it was like chromium dioxide or something like that. And those flecks, when you bring a magnet nearby, there's a torque that would make them rotate and align with the magnetic field. And so the information was actually stored by making those little things. You put a magnetic field that's pointing this direction, they all line up this direction. And then you make the magnetic field point this direction, they all line up the opposite direction. And so they stored the information by the direction those magnetic fields were oriented. Now, of course, what happens if you bring a strong magnet? The gel is soft so that they can rotate. If you bring a strong magnet next to your cassette tape, what's it going to do? It's going to destroy them because it's going to make them all rotate to face it. Question?
So how do people figure that kind of thing out? Like, how did that process?
Well, it could have come from historically looking at the Earth's magnetic field. Sailors noticed that their compasses didn't work very well when they were crossing certain parts of the ocean. The compasses would start changing around. And so you know the scientific process, you know something interesting, scientists are going to dive in, try to figure out what caused it. And what they found is that the ocean floor is like that cassette tape. The ocean floor has some regions where the magnetic fields are going like this, and then regions where they're going like this, and so on. And they're changing. And that's because there is hematite, a mineral that contains iron in it, and that hematite will be aligned if you put it in a magnetic field because of the torques created. So you have molten rock that comes up, and that hematite aligns with the Earth's magnetic field at that time. The molten rock freezes, and the hematite can no longer rotate. And so they can read the ocean floor much like we read a cassette tape. So that could have been what gave them the inspiration. I don't know. Do we still use this technology? As Sarah Palin would say, you betcha. The hard drive in your computer, if you don't have a solid state drive, which most people don't these days, it's still kind of expensive, a standard hard drive has a bunch of platins, a bunch of metal discs. I think they're metal. And on those, but they make them out of something like aluminum. Aluminum is non-magnetic. And on that, they put the gel, and in the gel, they put the little magnetic crystals. And then they have a little right head that goes across the surface and puts a strong magnetic field in a small region and makes those little magnetic dipoles align. And that's how we store data on a hard drive. And then we come by and read it by coming by and checking what direction the magnetic field is. So we still use that process. We don't use it on cassette tapes. Don't even use it on VCR tapes anymore, right? We do everything on DVDs or Blu-rays. But the hard drive in your computer is still using this technology, unless you have an SSD. SSD stands for solid state drive. It's using transistors and the like rather than this. So that's ferromagnetic materials. But they're not the only magnetic materials. We also have paramagnetism, which is a really weak action like ferromagnetism. Ferromagnetic materials, you have a strong attraction between north and south. And so if I have something that is like this, something that is made out of a magnetic material but is not itself a magnet, it will be equally attracted to the north side or the south side of a magnet. Because the little dipoles will just align and then be attractive. Paramagnetic does that, but it's much weaker, but it aligns and becomes attractive. Everything in the world is diamagnetic. Now, I'm not going to show this video. It's a video of the levitating frog. But every material is diamagnetic. But diamagnetism is really weak. So unless a material is not paramagnetic and not ferromagnetic, we don't observe the diamagnetism. But the diamagnetism is diametrically opposed to ferromagnetism. So instead of you put it in a magnetic field and it's attracted, it's repelled. And water is a very common diamagnetic material. So you take a frog, like a human being, frogs are largely water. And you put that frog in a very strong magnetic field, and the diamagnetism pushes it away from the magnetic field. And so this frog in this picture is levitating in a magnetic field. And like I said, if you go to this video, got the link there, you can see the frog levitating and floating around. And as far as all of their research suggests, it doesn't do any damage to the frog. After all, it's basically every cell in its body is pushing the same direction. So it's not like it's, this part, the heart is being pushed really hard compared to everything else. It's not like that. Everything's just being pushed together. And it's levitating, which is totally cool. And you can do other things like you can levitate a strawberry, So that's what diamagnetism is. Now, for our purposes in physics class, you need to know what paramagnetism is and what diamagnetism is. You don't work with them at all. Just have to know that they exist, that not everything is ferromagnetic. but we're going to focus on ferromagnetic materials. So that's all you're going to get here. But I'm just glad in another class you had it. So let's move forward past this. I think that was the same, well, basically the same as the last slide. So how do materials actually have ferromagnetism? And the words here lead us just to the picture on the next slide. Come on, picture on the next slide. Oh, not on the next slide. Those words are just the descriptions of this. I should have taken them out. In a ferromagnetic material, you have domains. You have small little, think of them like crystals, where the magnetic fields are working together. So they all align together. But in a normal material, such as what this was before I started the lecture, those domains are just randomly oriented. If they're randomly oriented, what do you suppose the net magnetism is? 0. So it's not magnetic. Now, I've been having this sitting on things. Yeah, still won't stick anything. It's still not magnetic. Because I take it out of the magnetic field and those domains relax. So how can I make something a magnet? Well, I need to align those domains and make them stay aligned. So, a couple ways you can do this. How many people are MacGyver fans? Okay, at least 1, 2, yeah. There's an episode in the first season of MacGyver where MacGyver takes a tire iron, whacks it on something, and it becomes magnetic. Realistic? I mean, they used to make a big deal that everything MacGyver did was realistic. It could really happen. There really are the chemical elements in an acorn that you could use to make a bomb. You would just have to do a whole lot of work, or MacGyver knows. Theoretically, sure. If you bang that tire iron on the fire hydrant, you're going to have those little magnetic domains get jumbled. And there's a statistical chance that there will be more pointing one way than another way, and you'll have a magnet. How strong? There's virtually no chance that it's going to be strong enough to do anything at all. But you could make it magnetic. Another way that works a lot better is to put something in a strong magnetic field. So I had these two, and only one of them worked reasonably well. Where did I put that little here? So only one of them worked very well. Right? This here just won't pick it up. This one here will pick it up, but one side won't. What do I do to make it better? Well, the standard way would be to heat this up to what we call the Curie temperature. The Curie temperature is the temperature at which those domains are free to rotate. Then if I put a magnetic field and cool it back down, boom, I got a magnet. Another way is to just put it in a really strong magnet. So I put this in here, and this is a little electromagnet. I press the button and it makes a really strong magnetic field inside. I go, And now that I've done that, I made it much stronger. Isn't that cool? How did I do that? Because I put in a really strong magnetic field that was strong enough to make those domains align and actually physically move a little bit and stay aligned. Now this is not super hard magnetically. That means that it can, over time, start randomly fluctuating and losing its magnetic orientation. If you have something that's really magnetically hard, and those little magnets I gave you guys, hopefully you still have a few that exist.
Oh, we give back to you.
No.
They're up there. Yeah, you're right.
Those are magnetically hard. Those are very unlikely to lose their magnetism because you have to basically heat it up to get them to rotate. So that's how we can change the magnetic orientation. Now this thing here is pointing crazy directions. Why do you suppose it is? Yeah, because there's magnets sitting here. Let me take these away. We measure the Earth's magnetic field. What direction do you think the Earth's magnetic field should be pointing here? If it's coming from that geodynamo in the center, what direction should it be pointing here? The answer is it's north, but also it has some dip to it. So this here is a dip compass. You align it with this compass, and that tells you the angle. So the magnetic field here is going very steeply down into the earth at this point. It's only weakly horizontal, it's much more vertical. That is assuming that this thing is balanced. I have no way of telling if it's balanced or not because I have no magnetic free region I can test it in. So we use these to determine the Earth's magnetic field direction. I am out of time. Next class period, we will try to finish chapter 22. So go now through the end of chapter 22 for the concept quote. Coach. Huh? Oh, you're right. I do not believe it's in the schedule to review this semester. We're on a tighter schedule. Okay, have a good day. As Bob and Bill, or Bob and whatever Mackenzie would say, take off, you hoser.